All right, guys, here we go with another test. Okay, so, excuse me, let's see, where are we at here? Section 8.3, part 2. Okay. Um, and this is A. We'll probably have to have an A and B as well. And this is for both A and B are covering April 8th. Okay. Remember, April 9th is a Thursday, so we don't meet, and April 10th is Good Friday. So this will, between A and B, this will wrap up the week. Okay. 8.3 covers 4 tests. Okay. We at least talked about 3 of them in part 1. But now we're going to add this 4th one. And then in part 1, we kind of talked about each one individually. Now we're going to kind of mix everything together. We're also going to mix up stuff from the previous. So we're going to kind of mix all the tests together. Okay, but first, we have not talked about the limit comparison test. So let's write that down and talk about it, and then we'll mix them all up. Okay, so what is the limit comparison? Be careful because there's comparison and then there's limit comparison. A lot of similarities. Suppose that you've got the summation or the series of A sub n. That's your given, just like in the regular comparison test. And then you're going to have to choose one on your own. Okay, there's a benchmark that you choose. You choose. Oh dear. You choose. Okay, you're going to choose that. And they're both series with positive terms, okay? But now what we're going to do is we're just going to take the limit as n goes to infinity of A sub n over B sub n. Okay, we're going to do the limit. It gets a little messy because you have to divide, but it turns out okay. And that limit is obviously going to equal something, okay? If that limit, C, is a finite number and C is greater than 0. So basically, I don't know why they write this. This is basically if C is any positive number. Okay? Infinity doesn't work, negative numbers doesn't work. But as long as C, as long as my limit is a positive number, then either both series converge or both series diverge. Okay? And so if you know that your benchmark diverges, and you get at least a positive number for the limit, then this has to diverge. If you know your benchmark converges and you get a positive number for the limit, then it converges. Okay? C is not what it converges to. Okay? All we know is that it converges. That's all we know. All right? So notice they're both comparison tests because you're doing this benchmark thing. Here, you actually take the limit. Okay? All right, so let's try one. Let's take a look. Let's just take a look at an example, and then we'll mix it all together. Okay, so I'm going to put that there for now. I'll probably need it again, and it'll be long gone. But actually, yeah, okay. Let's take a look at this example. Okay, n equals 1 to infinity, 1 over 2 to the n minus 1. Okay, let's turn it so you guys can see it. Okay, let's just talk about, and I'm not miswriting this, even though I do that a lot. Let's just talk about the comparison test. Okay, let's see, is that the one I want? Yeah, the comparison test. Okay, let me look. Yeah. Okay, so I'm just going to do the comparison test. I'm not even going to get to the limit yet. So the comparison test says I need a benchmark. So this is my A sub n. And my B sub n, my benchmark, everything I'm going to go off of, B sub n, is going to be those first two. So 1 over 2 to the n. Okay, so I'm comparing 1 over 2 to the n. Okay. Now, we haven't seen this, so this is a good review. This guy, I'm going to rewrite it as 1/2 to the n. Okay. And now, this, does anyone know what this is? This is geometric. We haven't done that one for a while. This is geometric. What is the rule? And I'm going to give you the rule, so don't panic completely. Geometric says if the absolute value of r is less than 1, and remember it's r, okay, is less than 1, and my r is 1/2, it converges. Okay, so this goes back to geometric. But remember we said when we were doing comparison tests, most of the time, B sub n is either going to be p-series or geometric. So this is one where it's geometric. Okay, so my r, remember this is where I had to rewrite it. My r is less than 1, so it converges. Okay, now a side note, some of you may say, hey, this is n and this equals 1. Let me just rewrite this. Okay, 1/2 to the n. Remember, technically this is supposed to say n minus 1, but that's only to get the a value. Notice if I actually took the time to rewrite this correctly, remember if this is 1, this is supposed to say n minus 1, but all I would do is write 1/2 and then 1/2 n minus 1. So if I need an a value, then I kind of have to do this. But notice when I do this, my r is not changing. Okay, the only thing that's actually changing is the a value. So if I need an a value, I have to worry about this. But if I'm just looking at my r values, then I don't have to worry about this. But this geometric is where this situation does come up. So I thought I would remind you that. But the r isn't going to change. And if I'm just identifying geometric, and if I'm just identifying if it converges or diverges, all I care about is the r. Okay. All right. So now the comparison test says if my benchmark converges, then what has to happen? Then this needs to be even smaller. Okay, then that needs to be smaller. Okay, all right, but what happens here? Like if n is 3, I get 1/8. Okay, here I would get 1/7. If my bottom, this is when n is 3. Okay, if my bottom is smaller, my overall fraction is bigger. If my bottom is smaller, my overall fraction is bigger. You could also, if you want this, we know, right? This is 0.125, and then this is 0.1428. It keeps going on, okay? But if just look at this. Subtracting 1 is going to make my denominator bigger. No, I'm sorry. If I subtract 1, my denominator is going to be smaller, right? I go from an 8 to a 7. If I subtract 1, my denominator is going to be smaller, which makes the overall fraction or the value bigger. So this is false. Okay. So remember, if it converges, if my benchmark converges, this has to be the case. If it fails this, I'm back to square one. So what am I going to use? I'm going to use the limit comparison. Okay, so comparison test fails. Comparison test fails. Okay, so now let's go to the limit comparison test. Okay, limit comparison test. Now the good thing is this is not all for naught, because I still need, okay, so I still have this guy and I'm still going to use this as the benchmark. Okay, so that still all holds true. So I need to do the limit as n goes to infinity of a sub n divided by b sub n. Okay, so I'm going to do, I can fit it on here. I think we'll sneak it up. Well, but you need the problem. Okay, let's see. I might have to rewrite it. So let's do the limit as n approaches infinity. A sub n, so I need to be able to visually see this guy. A sub n is what? 1 over 2 to the n minus 1. And b sub n, remember I can write it like this or like this. I think I'm going to go back to this way. I'm going to do b sub n 1 over 2 to the n. Okay. Okay, so instead of dividing, I'm going to multiply by the reciprocal. So the limit as n approaches infinity my numerator, and then my denominator, I'm going to flip this guy over. Okay. All right, now I think we can slide it up because I got my A from here, and my A and B are still here. So even though I did the comparison test and it failed, remember some of this I didn't even have to do, I can still use all of this for the limit. Okay, so it's not complete waste. Let me rewrite this though, because this is now important. Okay, so now we're trying to figure out this. The limit as n approaches infinity, and this is what we had written, 2 to the n minus 1 times 2 to the n over 1. This is a variation. We've done this before, 2 to the n minus 1. We've actually done it when it's been n squared. When it's n squared, we're going to do the same thing here. We're going to divide everything, even though it's flipped, even though it's 2 to the n, we're going to do the same thing. We're going to divide everything by 2 to the n. Okay. All right, and let's take a look at that limit. The limit as n approaches infinity, this now becomes 1, this now becomes 1, and this stays. But now let's turn it so you guys can see it. We can get rid of this guy. All right, so now we can plug in bigger and bigger numbers. As we plug in bigger and bigger numbers, this bottom's going to get bigger, which means the overall fraction is headed towards 0. Okay, as the bottom gets bigger, the overall fraction heads towards 0. So I've got 1 over 1 minus 0, which gives me 1. Okay, now we have to pause. What does this 1 mean? Well, let's see, I don't know if okay. The limit comparison test says as long as I get some positive number, then they both either converge or they both diverge. Okay, so then we have to go back. I said that my benchmark converges, or I know that my benchmark converges, therefore my original problem converges, because they both have to do the same thing. If I get a positive number for my limit, and I'm doing the limit comparison test, then my problem does whatever my benchmark does. I kind of like saying that again. Let me say that again. If the limit, as long as I get a positive number, then my problem does whatever my benchmark does. If my benchmark converges, then this guy converges. Okay? It does not converge to 1. This 1 is just telling me that my benchmark and my problem are going to do the same thing, but we have no idea what it converges to. Okay? So what do I want to say? This, because this is a positive number, okay, because 1 is equals or is a positive number, then my original problem converges. And I'm okay on the test if you just write converges, then that converges. Okay, you don't have to write all this out. I just thought it'd be good in the notes to remind ourselves, when I write converge, what am I saying converges? Okay, all right, so that is the limit comparison test. Okay, so, all right, here we go, guys. We're now just going to do a bunch of problems. We're going to determine whether the series is convergent or divergent, and we're going to use everything that we know to try to answer these problems, okay? All right, so we're going to start out pretty straightforward, and then we're going to mix in some other things, but the straightforward ones actually go back a ways, so it's going to take time to do each one. All right, so let's take a look. Here we go. We just have a bunch. 5, 6, remember, 7, 8, 9, 10, 11, 12. I think I have 13, and remember, some can be done different ways. Maybe I'll at least mention the other ways, and that's if I see it. Every once in a while, I won't even see it. So you only need 1. Okay, n equals 1. Okay, so here's our. Oh, I'm gonna label them because otherwise, okay, and directions would help. But if we move it down. Okay, I'm gonna number it. I don't know what I said. Label. I'm gonna number them. Okay. All right. 2 over n to the 0.85. Okay. Now remember, this covers everything. Okay. This Do we know what this is? N to an exponent. N to an exponent, we got to start thinking n to an exponent. This is a p series. Okay, so on the test, I want you to write what it is. Hey, this is a p series. Now, you'll be able to look it up. I'm going to give you all the rules just because the test is kind of long, even though you have some time at home. But as long as you know this is a p series and you can look it up, the p series says that if p is, and what is p? P is 0.85. P is the exponent. If that is less than or equal to 1, it diverges. Okay. All right, let's try another one. Number 2. The summation of n equals 1 to infinity. And I'm doing n of negative 1.4 plus n, or no, I'm sorry, plus 3n to negative 1.2. Okay, make sure you get that copied. Okay, so this, I'm just going to make this 2 separate problems. For summation, it is okay to make them separate. So we're going to look at the summation of n equals 1 to infinity. And I'm going to write this as 1 over, because this is negative, n to the 1.4. Plus the summation of n equals 1 to infinity. I'm going to write this as 3 over n to the 1.2. What is this guy? This guy is p series, n to an exponent, n to an exponent. This is a p series. Okay. And my p is 1.4. If it's greater than 1, it converges. Okay. Same thing here. The 3 has no impact. In fact, I could even pull the 3 out here. This is n to an exponent. That's a p series. This is a p series. So we talked about this briefly in the first part. But so now we mentioned p series, so if you need to look back, go ahead. But p series, p is 1.2. This gives you a better idea of the p series. If that's greater than 1, it converges. Okay? If they both converge, the whole thing converges. Okay? All right. Good. All right, we're cruising along. All right, let's try, so directions for the rest of the time, determine whether it's converges or diverges, okay? Notice it doesn't say what does it converge to or what does it diverge to. Most of the time we can only just say, well, we know if it diverges, it's headed to infinity. So I should say what does it converge to, okay? Most of the time we can't answer that question. We know it converges, but we don't know what it actually converges to. All right, now, a few of these we're gonna have to write the rule on our own. So let's take a look. 3 is 1 plus 1/4 plus 1/9 plus 1/16 plus 1 over 25 plus dot, dot, dot. I know for some of you it might be harder to write the rule, but sometimes it's just a good reminder. Like when we see this, do we remember what's really even happening? So sometimes it's nice to actually see the problem written out. But what we're going to do is we want to try to write the rule. So where is my red marker? There it is. All right, so this is a sub 1, this is a sub 2, this is a sub 3, 4, and 5. Okay, so how do these compare? How do we go from, and sometimes I start, it's easier to see here because sometimes these kind of go away, right? But 2 to 4, 3 to 9, 4 to 16, 5 to 25, okay? So what is the rule there? 5 squared, 25. 4 squared, 16. 3 squared is 9. 2 squared is 4. 1 squared, if I had to put this over 1, I could, right? All right, so let's write it as a rule. Sum n equals 1 to infinity, okay? And this is 1 over, this is n, and I want to square it. N squared. This number down here is n. So 2 squared is going to give me 4. 3 squared, 4 squared, 5 squared. Okay. So hopefully that'll help a little, right? What is that? This is a p-series. My p is equal to 2. If it's greater than 1, and this you can look up, so you'll just have to look up the p-series real quick. If p is greater than 1, because I always forget this too, I always have to look. If p is greater than 1, then it converges. Okay, and that's all you have to do. You have to identify a few things like this on the test, and then say that it converges. All right, let's try, I think there's one more. I think there's one more. So example 4, we got to come up with a rule on our own as well. 1 plus 1 over 2, the cube root of 2. 1 over 3, the cube root of 3. 1 over 4, the cube root of 4. 1 over 5, cube root of 5. Okay, let me get my hand out of the way. Okay, so we need to see, can we come up with the rule? Remember, oh, I think, is there one more of these? Yeah, there is actually one more of these. All right, so this is a sub 1, this is a sub 2, this is a sub 3, this is a sub 4, this is a sub 5. Okay, so this one might even be easier than this one, right? We can see that the rule is n equals 1 to infinity. Top is 1, okay, we can deal with that. And the bottom, the 5, is here and here. So we want to write this as, this would be what? This is going to be n to the first, right? Because this is 2, that goes right in there. We could just write n if we wanted to. And then times, this would be the cube root of n. Okay. This number just literally goes here and here. Okay. So we've got an n. If you don't put it the first, that's okay. And then we also want to take the cube root of n. Okay, so let's clean that up a little bit. N equals 1 to infinity. Now we could put the 1 there, n to the 1 times n to the 1/3. When you're multiplying, what do you actually do with exponents? When you're multiplying, you actually add exponents, so 1 1/3 or 4/3. Okay, so 1 over n to the 4/3. What is that, guys? That is a p-series. P-series, p is 4/3. If it's, and then this you can look up real quick. If it's greater than 1, can you guys see? Yep. If it's greater than 1, it converges. Okay. Let's do another one. Okay. All right. This one is example 5. Okay. Here we go. 1 plus 1/3 plus 1/5 plus 1/7 plus 1/9 ... Okay. We want to know, what are we trying to find out here? We want to know, if we add these all up, does the answer just keep getting bigger and bigger and bigger? Which, let's face it, most of the time that happens, okay? But there are a few cases where even though we add up a whole bunch of numbers, it approaches the sum. The sum actually approaches a number, a value. Now, when we say it converges, we're saying that, hey, this adding approaches some number. The only time we can say what that number actually is if it is a geometric series or if it is a telescoping series. Otherwise, we can say that we know this adding approaches some number, but we can't guarantee what that number is. All right? Okay. So first, and this one's a little bit harder. This is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. So don't completely panic if you don't see it. I'll try to do one on the test. I think even this one's a little bit harder, especially because we haven't practiced this at all. 5 to 9. Now remember, you might see it this way, but we want to see it this way. Okay, we want to use the 5 to get the 9. We want to use the 4 to get the 7, 3 to get the 5. Okay. Here, if I add 2, but here I have to add 3, here I have to add 4, that's going to keep changing. There's maybe something we can do with that. Notice, I think the easiest thing, but you have to see it. 5 times 2 is 10. I only want 9. 4 times 2 is 8, but I only need 7. 3 times 2 is 6. I only need 5. 2 times 2 is 4. I need 3. 1 times 1 is... no, I'm sorry, 1 times 2, right? I'm taking it times 2. 2 times 2. 1 times 2 is 2, and then take 1 away is 1. So my summation, n equals 1 to infinity. The top is 1. I'm going to take this times 2, but then I need to subtract 1. 2 times 2 is 4, but then I really only need 3. 2 times 1 is 2, but I would really write my bottom as 1 there, so I really only need 1. Okay. Don't completely panic. Like I said, if you don't get that, you'll be okay. Okay, any ideas what to do here? I will tell you that you can use the integral test. If you'd like to see the integral test, we could do that. And I'm not sure which one's easier. I think since we kind of have done improper integrals before, I'll let you kind of work on that. If you want to see it done, let me know. But we can also do the comparison test. But it's not wrong if you say, hey, I want to do the integral test. Again, because this is an end of the first and then this is no end of the 0, so to speak. That's kind of when you can use usually the integral test. All right, the comparison test, though, we need a benchmark. Okay, so benchmark, we need b sub n, and we usually use those first two, 1 over 2n. Okay, so let's rewrite it like this. The summation, we don't even necessarily have to put those others, 1 over 2 to 1 over n. All right, what do we have, guys? This is a harmonic. We could call it p-series, but if it's 1 over n, we can also, it's a special p-series harmonic. And harmonic always diverges. Okay, so this is my benchmark. This is my original problem. If this diverges, okay, if this diverges, and you can look it up. I don't know if I have it. Somewhere I have it. There's the limit one. Okay, here it is. And again, so on the test, you will be able to look things up because there's still a lot of stuff that you need to know in your head. So the comparison test, so if it diverges, then this has to be greater than or equal to. Okay. So is this true? Is this true? Well, if I subtract 1, I'm making the bottom smaller. If I make the bottom smaller, this is smaller, denominator is smaller, which means the overall fraction is bigger. Okay, if I make the bottom smaller, the overall fraction is bigger. If I make the bottom bigger, the overall fraction is smaller. Fractions always have to be difficult, right? But okay, so because this is smaller, this guy is bigger, so this holds true. All right, what does the comparison test say? If this guy diverges and this is true, if b sub n diverges, and again, you don't have to write this, but I just want you to see it in your notes. If this diverges and a sub n is greater than or equal to b sub n, then this guy diverges. Okay, then this diverges. All right, so I'm okay. Let me circle what you don't have to write. So you would just have to say this. You would have to say something about like this is true. You don't necessarily have to say any of this. You could then just write the word diverges. So what's in red is just more for notes, just more for your brain. But I'm okay if you write, hey, this diverges, this is true. So you have to identify this. Overall, it diverges. All right. So that one kind of popped up. Oh, and remember, if you want to try it with the integral test, you could do that as well. Okay, let's take a look at number 6. How are we doing on time? Let's stop and then, but we'll just keep going. All right, it's just like I said, we definitely could do 20 more minutes, but it's just it just goes so much quicker on YouTube to download something smaller. So let's stop there. But then we'll just pick up with more examples. In fact, B will be example 6. Okay, we'll just finish off with a few more examples.